We're going to look at the different kinds of discontinuity. And let me show you guys a picture. There are three kinds of discontinuities. And so here I've got a little picture. Now I'm going to do this over here. So we have three types of discontinuities. We have what's called a removable discontinuity. And a removable discontinuity is when the limit as x approaches c of your function exists. So if it exists, but it's not equal to f of c. Okay, so basically, so if at any point the limit exists, but the limit isn't equal to the value of the function, then that's going to be a removable discontinuity. So if you look here, you ask yourself, okay, where does the limit exist, but it's not equal to the value of the function? Well, that would be right here, because notice that the limit as x approaches 4 from the left and the right, both from the same, from both directions, it's equal to 8. But the value of the function at 4 is equal to this guy right here, 3. So because those two are not equal to each other, then that's called a removable discontinuity. Okay, now the second type of discontinuity is called a jump discontinuity. And that is when the limit, so you would have a jump discontinuity if the limit as x approaches c from the left isn't equal to the limit as x approaches c from the right. So if the limit of those two functions are different, then that's going to be called a jump discontinuity. And intuitively, you can see, obviously, this is the spot where you have a jump discontinuity, because if you come in from the left, so here, for example, at 6 from the left, this is equal to 1, and 6 from the right, the limit is equal to 9. And so those two are not equal to each other. So that would be a jump discontinuity right here. Okay, and then the last type of discontinuity is a infinite discontinuity. And so the infinite discontinuity is if the limit as x approaches c is equal to infinity or negative infinity. So you can see that you've got this situation right here at 8, because from the left it's going to negative infinity, from the right it's going to positive infinity. So at 8 there would be a infinite discontinuity. So those are the three types. Remember that a function is, so I already gave you guys the definition, but it's important to make sure that you know that a function is continuous if the limit as x approaches c of f of x is equal to f of c. So this is the definition of continuity. And all it basically says is if the limit is equal to the value of the function. So notice that, for example, I'm just going to pick a random point. Let's just say at x equals 2. To check to see if it's continuous, what you would do is find the limit. So you go, okay, from the right and the left, that limit is equal to 2. Okay, check. Then you find f of 2. And you go, oh, f of 2 is 2. So those two are equal, so that means that this function is continuous at x equals 2, for example. And, of course, this would work at 1, at 2, at 3, at 4, all those spots in between, except at 4, 6, and at 8. Okay, so here we have an example. What we want to do is find the discontinuities of this piecewise function. Now, because this is a piecewise function, there's a possibility for there to be, no matter what functions these are, there's a possibility for there to be a discontinuity where one of these functions ends and the other one starts. So if you look at what you want to do is look at first each function individually and see if they have any discontinuity. So for example, you know that 1 over x, you know that x can't equal to 0 here because that would make this undefined. And if you remember the graph of 1 over x, this would be an infinite discontinuity. But notice that you're not using this function for the value 0. It's only between 1 and 3, so you don't really have to worry about that. The same thing with this one. Because it's square root of x minus 3, you know that x minus 3 can't be less than 0. But, so in other words, x has to be greater than or equal to 3, but notice that that's where this function is defined anyway. So again, you don't have to worry about that. But that is something that you want to check. Okay, now once we did that, then what we're going to do is we're going to check the spots where a function starts and ends. So we're going to check x equals to 1 because that's when it goes from one function to another. And we're going to check x equals to 3 because that's where it goes from the second function to the third function. Okay. So remember the definition of continuity. So our function is continuous at a value c if its limit is equal to the value of the function. So all you have to do is, so for example, for x equals to 1 that we're checking, we just need to find these two things and check to make sure that they're equal. So let's do the easiest one first. Let's find f of 1, which is equal to, so here, which one do you use? Do you use x or do you use 1 over x? Well, which function is defined at the x value 1? Well, it would be this first one, right? Because it's x when x is less than or equal to 1. So you would plug 1 into x, which would give you, oh, just 1, sorry. That was silly. Okay. Then, once we do that, then we find the limit as x approaches 1. Now, for this limit to exist, and especially because it's a piecewise function, we need to check the limit coming from the left and the limit coming from the right. Okay, now for the left one, the limit as x approaches 1 from the left, that means that the values of x are less than 1, which means that when choosing which one of these to use, I'm going to use this first one because this one is defined for values less than 1. So I'm just going to plug 1 into this function right here. So basically you're trying to figure out which one to use. Now for this one, if you're coming from the right, approaching 1 from the right, that means the x values are greater than 1. So which function is defined for values close to 1 but greater than 1? Well, that would have to be this one because it's defined between 1 and 3. So then I would plug in 1 into 1 over x, and this would give me 1. So notice that the limit as x approaches 1 is from the left and the right. Those are equal, so check. And then they also equal to the value of the function at 1. So that means that this guy is continuous at 1. Continuous at x equals to 1. Okay, now let's try the next one, the value of 3. So to check at 3, what we want to do is we're going to compare 3 things. We want to compare f of 3, just like we did in the previous example. The limit as x approaches 3 from the left, and the limit as x approaches 3 from the right. If all 3 of those are equal, then it's continuous. If not, then it's discontinuous, and we have to say what kind. Okay, so the easiest one to do is f of 3, because all we have to do is plug 3 into the one that is defined for x equals to 3, and that would be this one right here. So I would plug in 3 into this guy because it's defined for x equaling to 3, and so here I get 0. Okay, now the limit as x approaches 3 from the left, that means that I'm going to use values that are less than 3, which means, but close to 3. So that means I have to use this guy right here. So this would be 1 over 3. So you can already see that it's not going to be continuous. But let's find this one so that we can make sure what kind of discontinuity it is. For this last one, we want to look at values of x that are greater than 3, which means that I'm going to use this guy right here. So square root of 3 minus 3, which is 0. Okay, so notice that this one, because these two are not equal to each other, the limits from both the left and the right, that means this is going to be a jump discontinuity. So it's continuous at 1, but discontinuous at 3, and the type is a jump discontinuity.